Dear students, in this class we discuss what is known as linear correlation, a concept which is closely related to linear regression, though it is different from regression. We often hear statements pertaining to correlation between two variables. As an example, we used to hear there is a positive correlation between advertisement expenditure and sales. There is a negative relationship between intelligence quotient and alcohol consumption. Or we talk about lack of correlation between any two variables. Now there are several statistics to measure correlation or lack of correlation between any two variables. The most commonly used measure of correlation is the linear correlation coefficient denoted as R. The linear correlation coefficient denoted as R, also known as Pearson's product moment correlation coefficient. Correlation coefficient. Pearson's product moment correlation coefficient. And for a set of data points on x and y, this correlation coefficient is defined as 1 by n minus 1 into sigma x minus x bar sigma xi minus x bar into yi minus y bar divided by sx into sy. For a set of observations on x and y, the linear correlation coefficient is defined as 1 by n minus 1 into sigma x minus x bar into y minus y bar by sx into sy, where sx is equal to root of sigma x minus x bar square by n minus 1. Sy is equal to root of sigma y I minus y bar square by n minus 1. That is the standard deviations of x and y. Now, since this is the numerator is a measure of association, covariance, as we divide this with the standard deviations Sx and Sy, we can show that R always lie between 0 and 1. Always lie between minus 1 and plus 1. R is also independent of the choice of units or units of measurement. R is independent of the unit of measurement, that is whether x and y are measured in kilo, quintal, gram. Correlation coefficient is not affected. The second is R always lie between minus 1 and plus 1. And this results from the properties of variances and covariances. If you want a formal proof of these statements, you just go through my class on correlation coefficients given in econometrics. a proof of this statement. yr is between -1 and +1, and yr is independent of the unit of measurement, etc. are given. Now let us see what are the properties. As I said, r is independent of the unit of measurement, always lie between -1 and +1. Always lie between -1 and +1. Independent of unit of measurement. In addition to this, there are some other important properties of this correlation coefficient. Remember that R measures the strength of linear relationship between two variables. The properties are meaningful if and only if the scatter plot of x and y is scattered around a linear line or a straight line. Remember this, it is a measure of linear association only. So if you have data on x and y, and suppose that you plot it, and if the scatter plots are like this, then only it is meaningful. Otherwise, it is not meaningful. And R reflects the slope of the scatter plot. R reflects the slope of the scatter plot. If the scatter shows a positive slope, R is positive. If the scatter shows a negative slope, R is negative. And if the scatter is widely scattered in the xy plane, then R is equal to 0. Now, why we have such a result? To explain this, consider this graph. This is x bar, this is y bar. Let in the numerator 1 by n minus 1 into sigma x minus x bar into y minus y bar, the numerator of the formula for correlation coefficients. Now you can see that if most of the points are in the first and third quadrant, you have a positive value in the numerator. Denominator is always positive. Similarly, if most observations are in these quadrants, you have a negative value in the numerator. So, and here also, if you want additional points, you refer to my class video on correlation coefficient posted in the playlist for econometrics. So, if the most of the observations are in 1 and 3, positive R, negative R if most observations are in 2 and 4. If the observations are widely scattered in all the quadrants, there is no association between x and y, and R is 0. And the magnitude of R, the value of R, indicates the strength of linear association. If R is 1 or close to 1, plus or minus, very strong linear association. If it is close to 0, very weak linear association. R is equal to +1, plus means positive correlation, minus means negative correlation. Now, in the form of graphs, suppose that x, y plots are on the straight line. R is equal to 1. X, y plots are close to the straight line. Close to R is, say for example, 0.9. Then widely scattered. So for example, R is equal to 0.4. Then R is minus 1. R is equal to minus 1. Close to R is equal to minus 0.9. Then widely scattered, R is equal to minus 0.4. It is like this. Now this is linear correlation, and we will not consider examples manually, as softwares will easily estimate correlation coefficients for us. So we have the formula we have discussed is the defining formula. For the computing formula, R is equal to sigma xy xi minus sigma xi into sigma yi by n divided by root of sigma xi square minus sigma xi the whole square by n into sigma yi square minus sigma yi the whole square by n. This is the computing formula for calculating linear correlation. And remember this, it is a measure of linear association only. R0 does not mean that x and y are not related. For example, suppose that the relation is like this, non-linear relationship. Of course, x and y are related, but the problem here is x and y are non-linearly related. So here you will get the value of R as equal to 0. So 0 correlation does not mean that the variables are not related. It only means that they are not linearly related. Another point is, correlation does not mean causation. Correlation between two variables does not mean that x is the cause of y or y is the cause of x. It is also possible that there will be a correlation between two variables, because these two variables will be correlated with a third variable known as lurking variable. And more about simple correlation, partial correlation, etc. are given in my playlist associated with the econometrics. So you can refer to that for more additional details.